This research project was supported by the Center for Advancing Transportation Leadership and Safety. It is a collaboration between the University of Michigan Transportation Research Institute, AMTRI, and the Texas A&M Transportation Institute, TTI. The Manual for Assessing Safety Hardware, also called MASH, specifies guidelines for crash testing and gives evaluation criteria for roadside safety devices based on what is called the place-based model. Better prediction of occupant injury is possible with the use of anthropomorphic test devices, or ATDs, which are also commonly called dummies. ATDs have a human-like response to impact, and they can be equipped with instrumentation, which can be used to assess the potential for injury in different parts of the body. In this study, attempts were made to compare real-world occupant injury risk associated with MASH criteria with injury criteria used in the U.S. New Car Assessment Program, also called NCAP. The main objective was to investigate the relationships between the occupant risk determined according to MASH criteria and the ATD injury metrics defined by the US NCAP and the FMVSS standards. In addition, a finite element model was developed and calibrated to nearly replicate the test scenario. The developed model can also be used in future for parametric studies.
Michi introduced the flight space concept back in 1981 in an attempt to better define occupant risk criteria for evaluation of roadside safety devices. The flight space model assumes that occupant as an unrestrained point mass, which in case of an impact acts as a free missile inside the occupant compartment. With this model, measured vehicle kinematics are used to compute the difference in velocity between the occupant and the occupant compartment. At the instant of occupant impact, the largest difference in velocity is termed as occupant impact velocity, or OIV. The occupant ride-down acceleration is the maximum 10 millisecond moving average of the accelerations subsequent to the occupant impact with the interior. This is also called as ORA. MASH sets limitations for both these occupant risks. A maximum value of 40 feet per second is allowable for OIV and 20.49 G for ORA. The flight space model, however, is known to be conservative in its nature due to the fact, for example, that it is not considering in any way inclusions of passive restraint systems such as seat belts and airbags. On the other side, vehicle safety is evaluated through crash test procedures specified in both FMVSS national standards and NCAP star rating program. Part 1 of FMVSS 208 standard defines crash test guidelines used to assess occupant protection during the vehicle impact against a rigid barrier at 30 mph. The FMVSS and US NCAP testing procedures use anthropomorphic test device, also called as ATD, to evaluate occupant injury risk at body region levels. The injury probability measurements are then compared to injury assessment reference values, so-called IARVs, which represent thresholds for acceptable injury risk. These thresholds are used to define pass or fail criteria for a test. For example, the maximum chest deflection acceptable is considered to be 63 mm. This is the IARV value for chest body region. If a chest deflection greater than 63 mm is recorded during a crash event, the occupant risk would be considered not acceptable because it means that there is a much higher chance for a higher injury severity in the chest region.
A frontal crash test was performed with a Toyota Yaris vehicle model, impacting a rigid wall at a 90-degree angle and at a speed of 35 mph as per NCAP guidelines. An H3 ATD was placed in the driver position and was restrained with seatbelt. The car was instrumented as per MASH standards. During the crash event, an occupant impact velocity, or OIV, of 56 feet per second and the maximum 50 millisecond average acceleration of almost 31 g were recorded. The OIV was clearly above the prescribed mesh limit of 40 feet per second. This translates to a high risk of occupant injury. However, when the ATD, HIC, chest deflection, neck, and femoral forces were evaluated, they were all well below the YARVs. Mesh values suggest a failure of the test with respect to occupant risk. At the same time, however, all recorded ATD injury values were well below the allowable limits, which indicate that the occupant was not at risk of serious and life-threatening injuries. These results and comparisons suggested that mesh evaluation criteria are conservative in nature and could be reevaluated for specific situations. Therefore, in specific situations, the researchers suggest that when the recorded occupant injury velocity is beyond the value of 40 feet per second, attention should be given to the recorded maximum 50 millisecond acceleration average. And the researchers also would recommend setting an allowable limit of 31 g to the maximum 50 millisecond acceleration average. This decision of this value is directly related to the recorded results from the performed crash test. Therefore, researchers suggest that if the longitudinal component of the 50 millisecond acceleration average is below the proposed 31 g limit, the occupant would not be at risk of serious and life-threatening injuries. And in those cases, for specific instances of barrier deployment, the test should still be considered a pass.
There is an existing finite element model of 2010 Toyota Yaris vehicle. An FE model of anthropomorphic test device, the ATD, was restrained with seatbelt and airbag in the vehicle model. An FE model of airbag is used to replicate inflation and deflation of a realistic airbag. The mass flow rate of inflation curve and the deflation curve of the airbag model was parametrically modified to best replicate test results recorded during the full-scale crash test event. Additional considerations were adjustment of driver's seat and ATD position according to the US NCAP guidelines. The complete FE model was then employed to replicate the rigid barrier frontal test. The vehicle and ATD kinematics well replicated the crash test. The developed FE model can be employed for parametric simulations with different impact conditions in terms of speed and angle.
Further efforts are suggested to calibrate and validate the developed complete FE model of the occupant, vehicle, and restraint systems. Investigation of occupant injury risk correlation can be performed for cases with different impact speeds and angles. Additionally, similar study can be conducted to determine correlation for occupant injury risk in frontal impacts with employment of a pickup truck vehicle to verify if similar correlation results are obtained. Also, crash tests and simulations can be performed considering impacts of passenger vehicles against the roadside safety devices to determine occupant injury risk and correlate it to the pertinent evaluation criteria.